Hello everyone, welcome to my channel Chemistry is Fun. Today we will study organic chemistry and today's topic is some basic concepts of organic chemistry. So today first we will see about the electronic configuration of carbon and the excited state of carbon in which it actually forms the bonds, because we know that carbon is tetravalent. So basically, if we see organic compounds, they are mostly the compounds of carbon. So organic compounds are the carbon compounds. Now, if we see the ground state electronic configuration of carbon, it is 1s2, 2s2, 2p2. So from this configuration, we can clearly find that carbon should be divalent, because in P, you see it is 1s2, 2s2, 2p2. So it should be divalent, but it forms tetravalent compounds. This tetravalency can be explained only if we get some other sort of electronic configuration. How we get that? By excitation of electron from the s orbital to the p orbital of carbon. So when one electron is excited from s orbital to p, s becomes s1 because one electron is shifted, p becomes p3. So excited state of carbon is 1s2, 2s1, 2p3. Now in this case, all the three p orbitals are half filled, s is also half filled. So it can form four bonds. So from here we can explain the tetravalency of carbon. But here we see there is a probability that tetravalent carbon should form two types of bonds, because s orbital is half filled, p orbital is also half filled. But we know that the shape and orientation of s and p orbitals are totally different. So it should form two types of bonds by using the electrons in the 2s and 2p orbitals. But if we study the structure of methane, CH4, where carbon is bonded to 4 hydrogen atoms, we find that all the bonds are equivalent. So for that to happen, the orbitals of carbon which are participating in bonding should be equivalent. Now how it happens? It was observed that carbon atom does not form the bonds as such, like s separately, p orbital separately. Actually it doesn't happen. What happens is that 1 2s orbital and 3 2p orbitals mix together. After mixing we get new orbitals. These new orbitals are known as hybrid orbitals, and this phenomena by which we get the hybrid orbitals is known as hybridization. And after hybridization, the orbitals which we get are equivalent. So now all the bonds which will be formed will be equivalent. Now there are three types of hybridization which are found in organic compounds. They are sp3, sp2 and sp. So 1s orbital and 3p orbitals, if they participate, we get 4 equivalent sp3 hybrid orbitals. 1s orbital and 2p orbitals hybridize to give sp2 orbitals. 1s and 1p orbital together hybridize to form 2 number of sp hybrid orbitals. Now we know that in the atomic structure we have already studied that s orbitals are closer to the nucleus compared to p orbitals. So the greater s character of an orbital, the smaller it will be in size. Okay, greater the s character of an orbital, the smaller it is. So the decreasing order of the size of the hybrid orbitals is opposite. Okay, than the decreasing percentage. So greater s character, smaller it is. This is reasonable to expect. Okay, the decreasing order of size of the hybrid orbitals is actually opposite, sp3 greater than sp2 greater than sp. It is just opposite to that of the decreasing percentage of s character. Okay, so the decreasing order of size of the three hybrid orbitals is sp3. This is the expected one, what we expect, but actual size what we get is sp3 greater than sp2 greater than sp. Now for any given atom, more the s character in the orbital, lower is the energy of the electrons in that orbital. So p will be having the highest energy, then comes sp3. In sp3 25% s, 75% of p character, so then sp3. After that sp2, in sp2 percentage of s is more than compared to sp3. Then comes sp where it is 50-50 and least is s, which is totally s. So more is the s character in the orbital, lower is the energy of the electrons in that orbital. Next, electronegativity. If we see, the electronegativity of an orbital increases with increase of s contribution. So in case of sp, you see s contribution is 50 and p contribution is 50-50. It is half, 1/2 s, 1/2 p. Whereas in sp2 it is 1/3 s and 2/3 p. And in sp3 1/4 of s and 3/4 of p. So the electronegativity of the orbital will increase with increase of s contribution. So sp will be having the highest one, then sp2, then least in sp3. The orbitals after hybridization, when they overlap to form the bonds, hybrid orbitals overlap better because their orientation is such that they can go for better alignment and stronger bonding with the other orbitals. Alignment of the hybrid orbitals is in the favor of bond formation. Now on the basis of the size of the hybrid orbitals, sp should form the shortest and sp3 orbital should form the longest bond with any other atom, because in sp3 p character is more. Now what type of hybridization of orbitals in organic molecules will be there? It can be determined on the basis of hybrid orbital number rule. This states that every sigma bond and unshared pair of electrons which is unshared on an atom uses hybrid orbital. Now see, in case of sp3 hybridization, this is possible when any atom is having either 4 sigma bonds. You see this diagram, carbon is having 4 sigma bonds, or it has 3 sigma bonds and one unshared pair of electrons. You see there are 2 dots I kept here, these are which I have drawn on the carbon. These are 3 sigma bonds and one unshared pair of electrons. This represents sp3 hybridization. In case of sp2 hybridization, atom can have 3 sigma bonds and 1 pi bond. 3 sigma bonds and 1 pi bond, you see here. This double bond means 1 sigma and 1 pi. So total there are 3 sigma bonds and 1 pi bond. Otherwise 3 sigma bonds and a carbocation, this one. 3 sigma bonds and 1 carbocation, positive charge. Or 3 sigma bonds and 1 unpaired electron. You see this is the dot represents the unpaired electron. So there are 3 sigma bonds represented by the dash and 1 unpaired electron. Otherwise 2 sigma bonds and unshared pair of electrons. This one, last one. 2 sigma bonds and unshared pair of electrons. Now see sp hybridization. sp hybridization will be possible when the atom has 2 sigma bonds and 2 pi bonds. When it has 2 sigma bonds and 2 pi bonds, it can be as a triple bond or as 2 double bonds. This is the case where there is a triple bond. This is the case where there are two double bonds on the same carbon. Or another chance is there are two sigma bonds and one pi bond. Two sigma bonds, here you see in this case there are two sigma bonds. This is one sigma bond, another sigma bond, and this double bond means one pi bond has to be there. Two sigma bonds and one pi bond and a positive charge on the carbon. Positive charge on the carbon. Or two sigma bonds and two unpaired electrons. This last one. Two sigma bonds. These single bonds are sigma bonds. And two unpaired electrons. These electrons represented by dots, they are unpaired electrons. So with this diagram, I think whatever statements have been given, they are explained properly. I hope you all could understand the topic which I discussed today. Thank you very much for watching my video. Please subscribe to my channel. Thank you all. Please subscribe to my channel. Thanks.